Hello everyone, welcome to video 5.2, Heating Effect of Electric Currents, part 2 of 2. And this is the problem that we left off with last time. We were solving series and parallel circuits. In fact, you may have seen my worked examples already where I solve a mixed circuit. If you haven't seen that yet, you're going to get a brief introduction to those kinds of circuits in this video, and then you can watch how the circuits are actually solved. Okay. So first, let's do this. So we're going to draw a schematic diagram for this circuit here. We've got 3 resistors in series, we've got 2 batteries in series, and connecting the voltmeter, you can see the dials on voltage, connecting the voltmeter across the leads of the resistor in the middle, we can see it's 1.06 volts. We have to connect voltmeters. So this is a multimeter, but it can act as a voltmeter, an ammeter, and an ohm meter. We have to connect the voltmeter in parallel to whatever device we're trying to measure. So here's what the circuit diagram would look like with the voltmeter. Notice that the voltmeter's leads, one goes on one side of the resistor, one goes on the other. It's called a voltage difference or potential difference because there's a voltage on one side of this circuit element and there's another voltage on the other side. When you take the difference between the two, you figure out how much is used up by this particular element. Always remember that voltmeters get connected in parallel to the circuit. All right, consider the following. We've got a simple circuit of just a battery, a lamp, and wires. If we want to measure the voltage of the circuit, you can just connect the leads of a multimeter to the ends of a battery. So this is the simple circuit that we have. There's the diagram. We've got the cell and we've got the lamp. Since we're measuring voltage, well, depending on what the voltage is, we might have to change the dial here, but right now it's set on 200. Okay, so it turns out, oh no, there we go, we're changing it to 20. Yeah, it's about 1.6 volts. Notice that the voltmeter is connected in parallel. Remember that whenever anything in a circuit is connected in parallel, it has the same voltage. So the voltmeter measures the voltage of the battery, and that is also in parallel with the lamp. So all 3 of these devices have the same voltage. Now something to note is some current does go through the multimeter when it's measuring voltage. Notice that the positive charge, and again that's unfortunate because that's the convention that we're stuck with, it should be negative charges that are moving through the circuit. But notice that the charge moving through the lamp is moving much faster than it's moving through the multimeter. So what that's meant to symbolize, and you can see it a little bit better here in the circuit diagram, is that there's a huge current, which is the regular current, going through the lamp, and a very, very tiny fraction of the current is actually going through the actual voltmeter. This we try to limit as much as possible. All right, to measure the current of the circuit, we have to break it. Now, with the voltmeter, we connected the voltmeter across, so in parallel to the device whose voltage we are measuring. But for ammeter, because it's measuring current, whatever current is going through a certain device, like a resistor, we want all that current to go through the ammeter as well. So as it says here, we want it so it intercepts all of the electrons that normally travel through the circuit. And so this is what the circuit diagram would look like. Notice that it is in series with whatever you want to measure the current of, which in this case would be the lamp and or the cell, which is the same. Okay, so this dial's got to get turned for current. Okay, so we're at the 200 milliamp setting. It's going to be a pretty small current. So notice that it is part of the circuit and the measurement is 0.2 milliamps. That's pretty small. Now, because it is in series, whatever charge it is that we're considering to be moving through the circuit, it's going to travel through the lamp, then the battery, then the multimeter, and then those exact objects in the same sequence again and again and again. All right, draw a schematic diagram for this circuit. Notice that it's broken, so that means most likely we're measuring the current. And sure enough, there go the leads. Okay, so remember that an ammeter gets connected in series. We've got 2 cells, so each one of these is 1.5 volts, so together it's 3 volts. We've got 2 resistors in series. We've got the ammeter in series with them, and then finally another resistor and the closed circuit. Because this is a series circuit to begin with, this 0.003 amperes, milliamperes that's getting measured, it just shows that that is the same current going through the first resistor and the second resistor and the third resistor. And that's the same current going through the ammeter. All right, now we've got what's called a combination circuit. Again, if you watched the second worked example, you would have already seen this. Actually, both worked examples had this. Now, with a combination circuit, you have part of it that's in series and part of it that's in parallel. And in order to figure out, well, what the equivalent total resistance is, you have to break it down one piece at a time. So in those videos, what I would have shown you is that you start with these two resistors on the left. You merge these two using the parallel resistance formula into a single resistor. Then that single resistor will be in series with this resistor on the top, allowing you to calculate the total resistance pretty easily. All right, ideally, the voltmeter should have infinite resistance. In other words, the resistance should be so high that no current will actually go through it. The reason being, we want the current to go through the original device because after all, we're trying to figure out the voltage drop across that device. By having the original current go through the device with its characteristic resistance, we can figure out the voltage drop. But if slightly less current goes through it, then there will be a different amount of resistance and therefore a different voltage drop, which is not going to be the exact reading. So what this green little box shows is it's showing the electricity, the current that is going through the circuit that goes through the voltmeter. Some of the current shown by the red box goes through the original resistor. It doesn't go through the voltmeter. What we want to do is make sure that most of the electrons go through the resistor and very few, if any, go through the voltmeter. So that's why we say ideally the voltmeter should have infinite resistance. Now, what about an ideal ammeter? The ammeter actually has the opposite property for resistance. It should not have any. Imagine the ammeter was not connected in the circuit. You would have three resistors in series. There would be some total resistance for the circuit. You've got a total voltage coming from the battery, and so you can find the total current, which happens to be the same as current through the first resistor, current through the second, and current through the third resistor. Now, if you stick an ammeter in there, if it has any non-zero resistance, it's all of a sudden going to increase the total resistance of this circuit. Because the voltage from the source remains the same, but the total resistance increases, that means the total current coming from the battery will decrease. So you're not actually measuring the true current going through the resistors because you've got this extra resistive device plugged in with it. So we want ammeters that have zero resistance, ideally. I'll leave this up for a moment. Okay. All right, so we've got a battery connected to a 25-watt lamp as shown. What is the lamp's resistance? Well, we need one more piece of information because we only have the power so far. So if we connect a voltmeter to the circuit, and again, we connect it in parallel with the battery because that'll also give us the voltage of the lamp. Okay, changing the dial, we get 1.4 volts. So going with that, we have power, we have voltage, we need resistance. So let's just pop over to the formula sheet. So we have power, we have voltage, we need resistance. So we're looking at this formula here. P is equal to V squared over R. So P is equal to V squared over R. And we're looking for R. So R is equal to V squared over P. So the voltage is 1.4, and that's in volts. And we're going to divide that by power, which is in watts, both SI units. Grab your calculator. 1.4 squared divided by 25. So 0.078, and that's going to be ohms. Okay, so there's our resistance. Back to the slides. All right, which circuit shows the correct setup to find the voltage current characteristics of a filament lamp? Okay, so what this is testing you on is, do you know how the voltmeter and the ammeter should be correctly connected in order to find the required quantities of the lamp. Okay, so the lamp is that X. Now let's start with A. Right now, the ammeter, while it is connected in series with the circuit, so right now what this ammeter would measure is the total current in the circuit because it's connected in series with the battery. Now, if we just imagine the current coming out, so the current comes out, goes through the ammeter, gets to this resistor, most likely this is a variable resistor, but whether or not, some of it will go through the resistor and then it will split, right? So part of the current will travel up this line and the rest of the current will continue down. And so the very fact that it splits, that means the total current that A originally measured is not going to be the same current that goes through X and then eventually joins with the original halved current and comes back to the source. I shouldn't say halved, I should say split because it really depends on their resistances. I'm going to show you C next. All right, for C, so we've got the current coming out. If you get to this resistor, there's a junction, it splits, so some of the current goes to the right, some of the current continues down through this resistor. The current that turns right, so when it gets to this junction right here, it's not going to be going any further, right? So it's actually not going to split again and go towards the ammeter because ideally this voltmeter has infinite resistance. So it's like there's a lot of traffic here and the traffic just doesn't move, not even 1 centimeter a second. It's not moving at all. So no electron is going to go straight, it's going to immediately turn right. And so whatever amount split from the beginning is going through the lamp, which means no current is actually going through the ammeter. Regardless, even if this wasn't an ideal voltmeter, even if it allowed a tiny amount of current to go through, that tiny amount that went through A as well is not going to be the same current that goes through the lamp. So C is also incorrect. Notice so far I've been able to use process of elimination simply looking at the ammeter. You could look at the voltmeter as well, but so far in part A, the voltmeter is connected properly to the lamp to measure the voltage. It's connected in parallel across it. Same with C, it's connected properly. Actually, same with D, it's connected properly here too. So let's see what's happening with A, the ammeter in part D. So we've got the current that comes out of the battery, gets to partway in the resistor and splits. Part of it keeps going down, part of it travels to the right. Now, whether or not a little bit goes to the voltmeter, that's fine. But a certain amount is going to continue towards this next junction. Now, I guess the real question is that a junction? Junction means there is a split in the circuit where some of the electricity will travel in one direction and the rest of the electricity travels in the other direction. But what you got to remember is that ammeters ideally have zero resistance. And even if they have a little bit of resistance, it's going to be so close to zero, almost negligible. So would the electrons rather go through a path of zero resistance or go through the path of the lamp where there is significant resistance? Well, if you guessed they would go through the ammeter, you are correct. That is the path of least resistance. This is the traffic that is moving. This is slow traffic. This is rush hour right here. Why would you take that path? Okay, so they're going to take 407. They're going to take the fast path here. All right, so that means, in fact, the electrons pass through here and they come back to the cell. So, sorry, actually what you're creating here is a short circuit. What that means, when you have a short circuit, it means that the electricity is just traveling very quickly through one route. There's nothing slowing it down. And usually when you say you have a short circuit in your house, the fuse goes off and the electricity shuts off for safety. Because if the electrons are traveling too fast, they will cause a lot of heat, a lot of temperature rise in the wires. It could potentially melt the wires and set fire to your house. All right, so long story short, the answer is not B. So let's go to B now. The electrons come out of the battery, they split. All right, so there's a certain amount of current going through the ammeter. And we get to this next part that looks like a junction. But remember, the voltmeter has a ton of resistance. So no electricity, no current is going to actually go past this junction. So it isn't really a true junction. It's just a new path. Right? So whatever current goes through A, the same current goes through the lamp. And it comes back here, joins with the original current. They merge and go back to the battery. So in fact, this ammeter measures the correct current going through the lamp. Not to mention, the voltmeter is connected in parallel across the lamp. So both are connected correctly. Now there are a lot of notes on this slide. Feel free to write them down if you'd like, but This is essentially what we just talked about. All right. Practice. A non-ideal voltmeter is used to measure the potential difference of the 20 kilo ohm resistor as shown. What will its reading be? All right, so this is interesting. And this question really requires you to think. We've got a 6.0 volt source. Now when the electricity comes out, so whether you consider coming out the left or the right, your mathematics are going to work out the same. All right, so let's say the current is coming out based on the conventional current direction. It's going towards the right first. When it gets to this junction, it's going to split. And this voltmeter, it's non-ideal because, well, look at the resistance. This is, well, first of all, it's not infinite. Well, how can you even have infinite in one of these problems? It would make the mathematics let's just say, very difficult. But this is the same resistance as the resistor. So from the point of view of the electrons, both of these objects are more or less identical. They both are going to slow down the electrons by the same amount. So we have to figure out what the reading is going to be. Remember, a voltmeter measures voltage. So we have to figure out what voltage is going to be here. So I'm going to go to my page now, and I'm going to sketch out this circuit. And I suggest you do the same. Or rather, well, if you have the paper in front of you, I guess you don't really need to. Okay, so... and we've got another side here. So that's our circuit, right? We've got 10 kilo ohms. This is 20 kilo ohms. And then we connect this voltmeter across, which just happens to also be 20 kilo ohms, and is going to fool the electrons into thinking it's a new resistor, because unfortunately the resistance is not that high. All right, so we've got minus, plus, so conventional current comes out, gets to the first junction, so this is I sub t, right, total current that comes out, and this voltage here is V sub t, the total voltage of the circuit. So the current gets to the first junction and it splits. Not just that, it splits exactly in half because the resistances are the same. So it splits in half, rejoins at this next junction. By the way, I keep using the word junction. I'll explain what that is towards the end of the video. It really is just a location where either the current splits or merges again. All right, so those merge again into I sub t, right, which then goes through the 10 kilo ohm resistor, and this goes back into the battery. All right, so I think a good starting point would be, well, let's figure out what the current is, the total current. In order to find the total current, I need total voltage and total resistance. And I don't have total resistance, so I'm going to look for that now. Remember that this voltmeter is essentially acting like its own resistor now, because, well, it has its own resistance, and it's exactly the resistance of the resistor in parallel with it. So I'm going to label these. So I'm going to call this resistor here 1, this one's 2, and the voltmeter, I'm going to call that 3. Okay, so it's going to have resistance R3. So what I want to do is merge these two. So I'm looking for R23. Now, since R2 and R3 are in parallel with each other, I know that 1 over R23 is equal to 1 over R2 plus 1 over R3. So 1 over 20 kilo ohms plus 1 over 20 kilo ohms. So that's 2 over 20 kilo ohms. That's 1 over R23. So then R23 over 1 is 20 kilo ohms divided by 2. So R23 is equal to 10 kilo ohms. So then the simplified circuit looks something like this. I mean, this is what it looks like from the electron's point of view. And of course, we could simplify that even more, but let's just see what we've got now. So we've got 10 kilo ohms and then 10 kilo ohms and 6 volts. Okay. Now we're going to merge those two together. Okay, so we're going to be getting R123, which is effectively the total resistance. Now, R1 and R23 are connected in series. So that means that RT, which is R123, is equal to R1 plus R23. So that's 10 kilo ohms plus 10 kilo ohms. which is 20 kilo ohms. All right, so I've got my total resistance, I've got my total voltage, I can find my total current. How? Using Ohm's law. So Ohm's law tells me that V is equal to I times R, so therefore I is equal to V over R. And of course I can put any subscripts that I want as long as they're consistent. So I sub t equals V sub t over R sub t. So that's 6.0 volts over 20 kilo ohms. All right, now for this, either you convert the 20 kilo ohms into regular ohms, or you actually just keep meticulous track of the units. I guess just to be consistent with my instructions, I'll change it to 20,000 ohms. So that's 6 volts divided by 20,000 ohms. Okay, so 6 divided by 20,000 is 3 times 10 to the minus 4. 3 times 10 to the minus 4 amperes. Okay, so what was the point of doing that? Well, I have the total current, and remember I said that total current splits here, and it actually splits exactly in half because each of these resistances is the same. So half the electrons will come here, half the electrons will come here. Not the best scenario when you're trying to measure the voltage here, but that's what we have in this case. So that means since R2 equals R3 and R2 is parallel to R3, therefore I2 equals I3, which is equal to 1/2 I total. All right, so 1/2 of that, that's going to be, so right now we have 0.0003 amps. Let me just make sure. If we had the decimal here, it would be 1, 2, 3, 4 spots to the left. Okay, that's correct. If we have that, so we're going to have 0.000015 amps. I'm just going to make double check of that. 3 zeros and 1.5 times 10 to the minus 4. 1, 2, 3. Oh no, sorry. 1 extra 0. Let's cross that out. 0.0015 amperes. Okay, there we go. 1, 2, 3, 4. Okay, so those are the currents going through resistor 2 and resistor 3. In order to find the voltage now through those resistors, and specifically we're trying to find the reading of the voltmeter. So we're looking for V3. I mean, this is what the whole question's been asking for. What's V3? V3, based on Ohm's law, is I3 times R3. Okay, so I3 is 0.00015 amperes times resistance 3, which is 20,000 ohms. All right, so 0.00015 times 20,000, 3 volts. So therefore, the voltage drop, or therefore the reading on the voltmeter will be 3 volts. Okay. Let's go back to the slides. All right, let's try this one. This will be our last problem on the slide, after which I'm going to show you how to handle more complex circuits. All right. All 3 circuits use the same resistors and the same cells. Which one of the following shows the correct ranking for the currents passing through the cells? All right, so we've got circuit X, circuit Y, and circuit Z, or Z. And we want to look at how these resistors are arranged. Since we want to know which one has the lowest current, which one has the highest, let's think about what that means. They all have the same voltage. They have the same source, so the same total voltage. Now, due to Ohm's law, we know that total voltage is equal to the product of total current times total resistance. You know what? I think we will use the page for this. Hang on. Let me just use this again. Okay. Ohm's law says total voltage is equal to total current times total resistance. We're trying to figure out which one of these has the biggest current. So total current is equal to total voltage over total resistance. They all have the same total voltage because they're the same battery. Now, what about total resistance? That's what you got to figure out based on the configurations that you see. Now, okay, let me just actually sketch it really quickly here. So we've got one scenario where our two resistors are connected in parallel with the battery. We've got another scenario where they're connected in series with the battery. And we've got our last scenario where we've got a combination series and then parallel. Some of you will not even need to work this out. You'll just be able to look at this and problem solve your way through, which is fine. This is multiple choice, so if it was a multiple choice test, you wouldn't be getting part marks anyways. So it's always good though to organize your work to try to figure out what the proper final answer would be. Okay, so they have the same resistors. So each of these is given the rating R. And like I said, we're trying to figure out which one of these has the biggest resistance. Whichever one of these has the biggest resistance, the biggest total resistance, well, you can see what's going to happen with the current. All right. So in this case, R sub x, since both of these are connected in parallel, 1 over R sub x is equal to 1 over R plus 1 over R. Common denominator, so that's 1 plus 1 over R, or 2 over R. So 1 over Rx. Okay, so therefore, Rx over 1 is equal to R over 2. So R sub x is equal to 0.5 R. So far that is the lowest resistance, right? Smallest number here. And so we get the biggest number over here. Well, that's the idea. Let's see what we've got. R sub y. These two resistors are in series, so we do R plus R. So R sub y is equal to 2R. That was pretty easy. Now the last one. First, we have to merge these two. Okay, so these two, this is going to be 1 over R prime is equal to 1 over R plus 1 over R, which is 2 over R. That's 1 over R prime, so R prime over 1 is equal to R over 2. So that's 0.5 R, and we saw that over here. When you have two in parallel, you get 0.5 R. So now 0.5 R and R are in series with each other. So then RZ is equal to R plus 0.5 R. So the resistance for Z is 1.5 R. Which means the highest current will be here, highest current, second highest current, and this will be the lowest current. Of course, when you have everything in series, you're not going to have very good current. So that means from lowest to highest, it should be Y, Z, X. Let's go back to our multiple choice selections. Y, Z, X, that is option C. Of course, all of that is explained on the slides as well, but there's the final and correct answer. Now, in lieu of completing the rest of the slides, I want to actually do this on paper because I feel like it will be better for you to learn it like this. All right, so our last type of circuit that we have to learn, because every other circuit that we've learned about, like I keep mentioning, has been covered in grade 9. So this is the next step, figuring out how to solve circuits where you have two sources of potential. So I've got two batteries and I got to figure out how to deal with these. Now, in order to solve circuit problems, and by solving a circuit, that means you have to find all the unknowns. So if a question ever says solve the circuit, that means you have to find all the currents, all the voltages, all the resistances. All right. So two sources of potential, find the current through each resistor and the potential difference across each resistor. In order to solve this kind of a problem, you have to use two laws, Kirchhoff's voltage law and Kirchhoff's current law. Kirchhoff's voltage law tells us that the sum of voltage rises and drops around any loop is equal to 0. Now, Kirchhoff's current law tells us that the current entering a circuit's junction is exactly equal to the total current leaving that same junction. I will explain how to apply these rules into solving this problem. All right, now the first thing you're going to want to do is figure out what's happening with the current in this circuit. All right, so the first step is pick either one of these voltage sources. Just pick one of them, it doesn't matter which one. And you're going to say that you have current I0 coming out of it. So because this is the positive side, that's negative, I'm going to say that my current I0 is coming out of here. Again, it doesn't matter which one you pick to start. All right, so I0 comes out of the battery, travels through until it hits this junction. So remember I said the word junction means kind of like a crossroads, a fork in the road. The current is able to either split or it's going from splitting to merging again into a single current. Okay, so we have I0 coming in. It'll split. Part of it will move forward, we'll call that I1, and part of it will continue down, we'll call that I2. Okay, so that means current I1 is going through the 9-volt battery, it's going through the 200 ohm resistor, and it meets up again with I2, they merge back into I0, and that goes back into the battery. And you could have just as easily started with this one, that's fine, but this is what we're working with. So based on everything I've done here in blue, I'm going to create an expression using Kirchhoff's current law. Okay, so I'm going to abbreviate that as KCL. So Kirchhoff's current law tells me that, looking at the picture, I0 is equal to I1 plus I2. I hope that's pretty self-explanatory. All right, so first step complete. We used Kirchhoff's current law. Next, we're going to be using Kirchhoff's voltage law. So his voltage law says that the sum of voltage rises and drops around any loop is equal to 0. So what I'm going to ask you to do is take a different color if you have one and draw a loop. Okay, draw one loop inside the left half of the circuit and draw another loop inside the right half of the circuit. And then label them. I'm going to call the one on the left A and I'm going to call the one on the right B. It doesn't matter where your loop starts and where it finishes. I could have started this loop on the right and ended it here just at the bottom underneath the 9 volts. Or I could have started it at the bottom and gone clockwise or counterclockwise. It doesn't matter because at the end of the day, it's a loop. So you're going to cover all the required pieces anyways. All right, so Kirchhoff's voltage law. Now we're going to look at loop A first. So I'm just going to put KVL sub A. All right. So, I mean, let's say I want to start here. I'm traveling along. This is current I0, and then I'm coming down here. What's happening? Current I2 is going through the resistor 100 ohms. And since we have our loop traveling in the same direction as the current, right? Because our loop goes up, right, down, left, up, right? So at this point, our loop is telling us to go down. So we are moving in the same direction as the current I2. Therefore, there's going to be a voltage drop here. Right? And you knew that already. When you have resistors and you have devices in your circuit, you experience a voltage drop, assuming you're moving in the direction of the current, which we are. When you move through a battery, when you go from the low potential to the high potential, minus to plus, you have a voltage gain. All right, so again, we're moving in the same direction as I2, and we're going through the 100 ohm resistor, so we have a voltage drop. All right, so voltage drop. All right, so let me just make a note here. So we have a voltage drop at I2 since our loop is moving in the same direction as I2, right? If it's in the opposite direction, it would be a voltage gain. Now, his voltage law says the sum of the voltage rises and drops is equal to 0. So we want to make an expression for the voltages. Now, using Ohm's law tells us that we can make an expression for voltage by taking the product of current and resistance. And that's what I want to do, right? So I have here initially a voltage drop. So that voltage drop is equal to I times R. So I2 times 100 ohms, right? So I2 times 100 ohms. That's my first voltage drop. And since it's a drop, I'm going to stick a minus sign in front of it. But this whole thing is voltage, right? Don't forget, this is a voltage drop, minus V1, you could call it if you want. Okay, next, so now we keep following the loop to see what else is happening. So we come down, left, nothing interesting so far, and then we hit the battery. And in order to move through the battery in the direction we've drawn the loop, we're going from minus to plus. So low electric potential to high electric potential, right? So we are gaining potential. We have what's called a voltage lift. Okay, so let me just make a note here as well. In loop A, since we are moving from low potential to high potential, this is a voltage lift. Okay, so this would be a drop, this would be a lift. Okay, specifically, how much are we gaining? We're gaining 1.5 volts. This is already in volts, so I don't have to take some product of current times resistance. And so I write plus 1.5. You can put the V if you want. It's getting kind of confusing now with all these letters, so I'm just going to say that that's equal to 0, right? The sum of the voltage rises, and the drops, which is this part right here, around any loop is equal to 0. So there's Kirchhoff's voltage law, part A. Now, Kirchhoff's voltage law, B. Same thing, start anywhere in the loop that you want. You don't even have to start where you started the loop in the picture. Okay, so in fact, I won't. I'll start over here. I'll start where the 9 volts is. So remember, the long line is the plus and the short line is the minus. So if we start here and we move in the direction of the loop, and notice that we're moving from high potential to low potential, that's a voltage drop. So let me just write that here. Here I have a voltage drop. And what is the drop? It's 9 volts. So I start off with negative 9 volts. Okay, so there I am putting the V, so I guess I'll just stick it in there too. All right, so negative 9 volts, and then we follow loop B. So now we're going through the 200 ohm resistor, and with the 200 ohm resistor, we are traveling in the same direction as I1. And since we are traveling in the same direction as the current, that means it's a voltage drop. Okay, so voltage is current times resistance, so that's going to be minus I1 times 200 ohms. Okay, so let's go back. So we go through this resistor, we come here. Now what happens with the loop? We go back up, and now we are going through the 100 ohm resistor based on the direction of the loop. However, this time our loop is telling us to move up, but the current going through this resistor is I2. It's going down. Since we are moving opposite the direction of the current, this is going to be a voltage gain. Okay, so we have 2 drops and we have 1 gain. All right, so what's the gain going to be? It's voltage, so it's current times resistance. I2 times 100 ohms. And since it's a gain, I'm going to write it like this. Plus I2 times 100 ohms. And all of this, running out of space, is equal to 0 due to Kirchhoff's voltage law, right? The sum of the voltage rises and drops around any loop is equal to 0. Usually with this type of problem at this point, you have 2 equations, these 2 equations in red, and 3 variables, I0, I1, and I2. In this question, it's a little bit simpler, so I actually only need these 2 formulas. Usually I would use the third formula to simplify one of these, creating 2 equations with 2 unknowns. I'll do a separate video for that, so you can watch that example in that video, but this is a little more of a simple example to get us started. All right, so in fact, we don't need this formula, but usually we do. It's always good to write it. All right, so from his first loop, Kirchhoff's voltage law A, I can actually figure out I2. So I'm going to have 1.5 volts is equal to I2 times 100 ohms. So then I2 is just 1.5 divided by 100. So what that means is I take this decimal and I move it to the left 2 spaces. So that's going to be 0.0015. Let me just, 1, 2, so that's going to be, I put 1 extra 0 again. I like doing that. 0.015, so this way it's 1, 2 spaces to the left. Okay, so 0.015 amps is I2. All right, so we've got that. Now let's find I1 using this formula. So we have -9 minus 200 I1 plus 100 I2 is equal to 0. Oh, you know what? We are actually going to use this formula in the end, so we can find I0. So actually, always write this no matter what. Okay, so we've got 100 I2 minus 9 is equal to 200 I1. So 100 times 0.015 amperes minus 9 is equal to 200 I1. So I1 is, okay, so 100 times that's just going to be 1.5. 1.5 minus 9, that's simple enough, negative 7.5, and dividing that by 200, so we have, oh, this is I1, is negative 0.0375. Now, it's important for me to point something out here. It's not unusual for current to be negative, and the reason for that is because current is a vector quantity. If you didn't realize that yet, it's got to be a vector quantity because you can clearly see it has direction, and direction matters. So it's okay for the sign to come out negative, but the fact that the sign came out negative just means that we chose the wrong direction for I1, and that's okay. Remember I said initially you have to choose arbitrary directions for your I0? That means the current isn't actually coming out of this battery, most likely it's coming out of this one. And so the direction for I1 is actually the opposite, which is fine. You haven't really made a mistake. And so this is what we're going to do. We're just going to put a little note here. We're going to say this came out negative because we just chose the wrong direction for I1. Okay, so it just goes the other way, which is completely fine, right? So we know that the current I1, if you were to actually state what the current is, you would drop the minus sign and you would just say the current is 0.0375 amps, okay? Just as I2 is 0.015 amps. However, that negative sign plays a crucial role when you're finding I0. So don't drop the negative sign just yet. In fact, I should probably do this in blue. When you calculate I0, you keep whatever minus signs come up in your original calculation. That's how you stay consistent. So I1 is 0.015 amps, and I2 is negative 0.0375 amps. So please keep that there. So 0.015 minus 0.0375, and that's negative again, which just means the direction for I0 is also backwards, which is fine. This is how we determine which direction the current is actually going. But you see, if you put a positive here instead of a negative, you would get the wrong magnitude for I0. And so we can say, therefore, the current through the 100 ohm resistor is, okay, so that was I2, 0.015 amps. And the current going through the 200 ohm resistor is, and that, so the 200 ohm resistor, that was I1, right? I1 was going through this. So I1 is right here. Just don't put the negative sign in this part. 0.0375 amperes. Okay, so there's part of our answer. And the reason I say part is because we still have to find the potential difference across each resistor. That part's pretty simple. Okay, so let's just do that quickly. In order to find the potential difference, that's essentially the voltage. All right, so if we want to find the potential difference across the 100 ohm resistor, then we find the current going through the 100 ohm resistor, which was I2, times that resistance. So the resistance of the 100 ohm resistor. I guess it's redundant to write it like that, but anyways, that's what we've got. And we want to find the voltage across the 200 ohm resistor, so that's I1 times R sub 200 ohms. All right, so I2 was 0.015 amps times 100 ohms. And this one is going to be 0.0375 times 200 ohms. See, not so bad. Oh, so 100 times this is going to be 1.5 volts, so that was easy. And 200 times 0.0375, 7.5 volts. So that's V 200 ohms, and this is V 100 ohms. Okay, so there we have it. There is the end of that example. Like I said, I'll do another video where I actually solve another one of these circuit problems, a little bit harder than this one, so you can get another feel for this kind of a question.